Welcome. Today I'm going to talk to you guys about one of our primary tools for calculating the speed and the acceleration when we're doing an experiment, and that is through a graph analysis. Remember in one of the previous videos we talked about how we oftentimes will graph our data, our independent and dependent variables, on something called a scatter plot. And so the question is then, once you have a scatter plot and a best fit line or a best fit curve, what do you do with that information to be able to get anything out of it? So this is our first technique to be able to get information out of a graph other than just being able to construct it. So we're going to see how that works, and specifically what we're going to try to find today is we're going to use the position versus time graph to find the speed, and the speed versus time graph to find the acceleration. Video 11 on slope 011, we are going to begin. Okay, so we're going to start off with just a quick discussion of what this should look like here. So my guess is during an experiment you would have an independent variable that is something like time right here, okay, and then a dependent variable that's something like position. Most often that's what we're going to do when we do motion experimentation in the class. So we'll have a data table that looks like that. Now, just a little point that you might want to, that you probably haven't thought about before. We're going to use Google Sheets a lot, and for Google Sheets to be able to accurately put the independent variable on the correct axis and the dependent variable on the correct axis, the independent variable usually has to go on the left. You can fix it if you make the mistake, but it's much easier just to do it right from the beginning. So I always put my independent variable on the left-hand side and my dependent variable on the right. And as you might imagine, time is oftentimes going to be our independent variable, and position will be our dependent variable. We're going to look where an object is located at different times. That's an experiment we're going to do quite a bit in here. So what do I do with that? Well, on Google Sheets or Excel or Graph Analysis or Logger Pro, or just by hand if you're so inclined, we would create an XY scatter plot. On an XY scatter plot, typically the independent variable goes on the x-axis, and the dependent variable goes on the y-axis. Now don't get confused by the fact that this is an x and it's on the y-axis. X means position. This is different than the x-axis, which means horizontal. So don't let that get confusing for you. Again, this is the dependent variable axis, and our dependent variable is x in this case. So don't get confused by that. Now let's imagine for a moment that we have a position best fit line that looks like this. So I'll change my color here so you can see this. So let's imagine that we have a best fit line that looks like this. Something along those lines. Okay, there we go. So my question for you is, can you take a look at each time? So we go down here and you figure out what the time is. Let's switch to blue right there. So let's say we have t sub 1 right here. So my question for you is, can you tell me where the object is located at t sub 1? Of course you can. Since probably middle school, you've been able to read graphs, XY graphs. So you know that at time 1, it should be at x1 right there. Now at time 2, let's say right here, time 2, we can see that the object is now at x2. And so I will try to draw that across here, like so. Okay. So my question for you is, how fast is the object going? And you may remember, hopefully you remember, since we've talked about it a lot now, that the formula for this is the average velocity, average speed, is equal to the displacement, or the change in position, divided by the change in the time. So you can see that it's going from here to here. That's our change in displacement. or that's our change in position, which is our displacement. And then it's also going from here to here, and that's our change in time. Okay, and so we're able to calculate that out. No problems, right? I want you to think about this for a second, though. Isn't that the exact same thing as the slope of that line? So let me just kind of remind you of your geometry class again, or your basic algebra class again. In your basic algebra class, you said that the slope of a line, which was m, and I don't even remember why it was m, so the slope of a line, is equal to the rise over the run, right? Or, if you want, it was the change in the y-axis over the change in the x-axis. Now, what does this look like? Well, doesn't it look like that right there? I hope so, because they're really the same thing. And so what I'm asking you to do when I find the speed of a position versus time graph is really just find the slope of the best fit line. And what we would say then is that the speed is the same thing as the slope. There we go. And so that's the way that it works. Now you can see that this is a best fit line, so the slope is constant, which means the speed is constant in this case. Hopefully that makes sense. So that's how we do it. It's pretty simple. Again, don't let the fact that this is a delta x, which means the change in the x-axis, and this is a delta x, which means a change in the position, confuse you. They're two different things, but they work together in this case to be able to give us our correct answer. So that's slope right there. So the rise over the run, right, will tell us how fast the object is going. And this is what we call slope analysis, and it's something that we do all the time, especially when we have a value that we're trying to get that has a ratio in its formula right here. So we have to make sure that when we do this, we put this variable on the x-axis and this variable on the y-axis to make sure that it matches up nicely with the slope of the line. And so this is why, quite honestly, this is why the independent variable almost always goes on the x-axis, because we have to make sure that ratios match up like so. Okay, now let's go ahead and move on to the next here. Now here's a question for you. What happens if the speed is not constant? Last slide you saw that the speed was constant, and you knew that because the line, it was a best fit line, so the slope was always the same. But let's imagine a situation that looks a little differently. Let's imagine that the object that you're talking about is speeding up. We would say it's accelerating. And so it would have a displacement versus time graph that would look like this. So this would be your position on the y-axis and the time on the x-axis. Now my question for you is this. When you take a look at this line, this curve right here, this best fit curve, you can see that at any one particular time, the slope of the curve is changing. So let's imagine for a moment that this right here is our T1, T sub 1 right there, okay? And that this right here is our T sub 2. And so my question for you is, first off, can you compare the speeds at T sub 1 and T sub 2? So what I'm really asking for is instantaneous speeds. So the instantaneous speeds would be like this. at t sub 1, how would I figure that out? Well, I want you to think about this for a second. Before, we said if you have a position versus time graph, it's the slope of the line that's going to tell you what the speed is. Well, at this one particular point right there, it's really hard to make a slope. But we can go ahead and imagine that we have a line that touches the curve just at that one particular point, like so. And so it's the slope of this line right here, this green line, that will tell us how fast the object is going. It touches the point, the curve, at one particular point. So we call that a tangent line. So the tangent line touches at only one point. Okay? So if you compare the slope here to the tangent line of the slope here, where it touches it at only one point, I did a pretty terrible job of that, but you get the idea. You can see that the slope of this line right here, this tangent line, is much lower than the slope of this line. How do I know that? Well, look at the rise over the run. This is how much it rises, and this is how much it runs. So you can see it rises a lot for a little bit of run on this one, whereas this is how much it rises here, and this is how much it runs there. And so you can see it rises a small amount over how much it runs. So you can see the slopes are different. And in fact, the slope for this one is lower and the slope for this one is higher. And so we say at time t sub 1, the instantaneous speed is lower than the time t sub 2. The instantaneous speed is higher. Okay, so I'll say that's lower. And at t sub 2, it's higher. Okay, now that's for instantaneous speeds. Well, what happens if you want to actually try to find an average speed, though? So an average speed is a little bit different. Remember, that's between a large separation of time. And so in this case, we would not find the average speed at t sub 1 or the average speed at t sub 2, but rather we would find, oops, I forgot to draw my arrow here. Sorry about that. This one's higher. There we go. So going back to this, the average speed would not be at t sub 1 or at t sub 2, but it would be between t sub 1 and t sub 2. It's my and symbol if you haven't seen it already. I know it's weird. So how would I find the average speed between those 2 points? Well, I could go ahead and go over, just like I did before, and try to figure out what the x value is for 2, and try to figure out what the x value is for 1, and then I could just do the math that way. Sometimes that's pretty easy. However, if I'm going to use the graphs the way that the graph should be used, I'm going to draw a line between the 2 points, like so, and then find the slope of that line. And so the slope of this line is going to tell us what the average speed is. Now, since it touches the curve at 2 points, we call that a secant line. So if I ever refer back to a secant line, you can go ahead and refer back to this to remember that the secant line touches at 2 points there, whereas the tangent line only touches at 1 point. Something like that. Okay, so that's how I figure out the average speed versus the instantaneous speeds. It's tricky. In fact, to be honest, finding the slope of a curve at one particular point is one of the reasons calculus was invented. I think I've talked to you before about the fact that instantaneous speed is actually something that calculus is best suited to answer. For us, we can estimate it by putting 2 points very close together and then drawing a line between the two. And that's really what we do, is we just estimate it. So again, instantaneous speed, actually quite tricky to figure out how to do it, unless you know calculus. If you haven't taken calculus, you aren't taking calculus, I would highly recommend that you do that. Um, just ignore the recommendation for Windows 10 down there. Sorry about that. Okay, so the last piece is this, and that is, get rid of this here. There we go. The last piece is this, which asks us to take a look at how we use this same method to be able to find the acceleration. Well, it's actually quite easy. So let's imagine for a moment that the data that you have is, again, time, but in this case now you have instantaneous speed. So you have instantaneous speed, so you have speeds at different times. So let's imagine that we have graphed this out on a scatter plot, just like we almost always do. We put the independent variable there, time, and we put the dependent variable here, speed, instantaneous speed. And again, the sub n right there just lets us know that it's instantaneous and not average. So if I had a graph that looks like this, that's my best fit line, you can see that the speed is increasing as time goes on. What we would say with the speed is increasing is that it must be accelerating. How can we figure that out? Well, remember that the acceleration formula that we learned a little while ago looks like this. The average acceleration is equal to the change in the speed over the change in the time. Now remember that a moment ago we talked about the fact that the slope of a line on a scatter plot like this is equal to the rise over the run, or the change in the y value over the change in the x value. Can you see, again, that these things are the same? I hope so. The y value is where we graphed out the speeds. The x value is where we graphed out the times. And so they're the same thing. And so to figure out the acceleration, all I would need to do was to figure out the rise and then the run. And then that would tell me how much the acceleration, we had on this object. It's pretty straightforward. It's just another way of thinking about it. If you're presented with a situation where you have a graph and you have to analyze that graph, this is the best way to do it. Oftentimes when you have a Excel spreadsheet or a Google Sheets spreadsheet, or you're using LoggerPro, you can get the program to tell you what the line is, what the equation for the line is, in y equals mx plus b form. That m that you see in the y equals mx plus b form is the slope. And so you can get the spreadsheet to do the math for you. And that's the lazy way of doing things. And quite frankly, it's the better way of doing things. So you want to make sure that you use the best way possible. So finding the slope this way would give you the slope, which would then give you the acceleration. That's easy enough. And for us, like I said in a previous video, we will almost always use constant acceleration. So you'll never see a speed versus time graph that has a curve on it, because that would mean the acceleration was changing over time, and we're not going to do that in this class. Okay, hopefully that makes sense. All right, with that, I want to thank you for watching. Don't forget to fill in those note sheets and the interesting question forms. Those interesting question forms are going to be crucial here as we move forward. How much slope analysis will we be doing in class? Quite a bit. So you want to make sure that you're familiar enough with it that you can replicate it. It will be represented on the test, actually, in a number of questions as well. And it will be on every test, or almost every test from here on out. So you want to make sure you know what you're doing. Also, just as a side note, it's great for increasing your scores on the science subsection of the ACT. They use that idea oftentimes in there. And if you have that tool in your toolkit, you have a pretty easy way of boosting up your scores. Okay, with that, I want to thank you guys. If you have any further questions, let me know. Good luck.